Hey, we're going to be looking at finding the average rate of change in this notation right here. I've got AVG for average and RC right here for rate of change. Here's our function f of x is equal to 5x plus 7. We're on this interval right here. So this is an interval between 0 and 5, and we're going to be using this formula right here. Now, as you can notice, this is just like the slope, right? The slope formula, y2 minus y1 over x2 minus x of 1. You're given 2 points in the plane and you're running a line through it and finding the slope of the line. So we call this, though, the average rate of change. Alright, well, let's work this out. So this is f of b minus f of a. So we're going to end up plugging 5 into here and then plugging 0 into it and getting their difference, and then it'll be over 5 minus 0. So here's our setup, f of 5 minus f of 0 over 5 minus 0, and we just plug the numbers directly in, as you can see here, and we end up getting 25 over 5, which is equal to 5. Now we're saying that the average rate of change is 5. If we were to look at the instantaneous rate of change, and I'll get to that here in just a minute, but you're going to take the derivative, and the derivative of our function is equal to 5, and then what we're going to do is plug one of our endpoints in, which is 0, plug it into the derivative. Well, you still get 5. You plug in the other endpoint and you still get 5, and that's because our derivative is equal to 5. No matter what you plugged in here, you're going to get 5. So the instantaneous rate of change, when x is 0 you get 5, and when x is 5 you get 5, but our average rate of change was also 5. Here's the graph of our function. Now we notice that it's just a straight line. So you're given 2 points, and you're basically saying, okay, we want to find the average rate of change between these 2 points right here. Well, because it's a straight line, we end up getting the slope of the line, which is 5. Now keep in mind, this is not a one-to-one scale here on my axis, so this is not going to be a true slope of 5. It would be a whole lot more steeper than this. But anyway, and then we did the instantaneous rate, and we got 5 at this point and 5 at this point, because the slope of the tangent line at this point is 5, and the slope of the tangent line at this point is 5. But that's all because we're just working with a straight line. Let's look at another example. Well, this time we've got x squared, so it's not going to be a straight line. It's going to be a parabola, and actually it's going to be concave down. Anyway, here's our interval. Remember, this is our formula that we want to use for finding the average rate of change. So we plug in f of 2 minus f of 1 over 2 minus 1, right? We're on the interval between 1 and 2. And so we do that, plugging 2 into the function, minus plugging 1 in, and doing the arithmetic, and we should come out with -9. So this time the average rate of change is -9. Now, if we took the derivative of our function, we get -6x. And if we evaluated it at 1, we get -6, and evaluating it at 2, we get -12. Now you notice that -9 lies somewhere in between. Okay, so we are between 1 and 2. Now the average between 1 and 2, the average, remember, was -9. If I looked at the slope, the instantaneous rate of change at 1, that slope, remember, is -6, we can barely see up here. And as the curve decreases or goes down, you can see that that slope of that tangent line is going to be even, well, I guess you could say greater, a greater negative, but it's going to be a whole lot more steeper. And then somewhere in here, there's actually a point on the x-axis. Somewhere in here, there is a slope on this curve right here. There is a slope of -9. So the average rate of change is going to always fall between 1 and 2. If it doesn't, you've probably done something wrong. Okay, well, you can go on and look at some more of these examples on how to find average rate of change, and in the next section we'll be talking about some applications.